Okay, SN1, E1 as an intermediate, not retention. Retention is also control. Inversion is also control. Okay, transition state. Partial chloride. 아, 안 바뀌어야지. 굉장히 처음 듣는 사람, 저 표정으로. Harassment is here. This attack. And intermediate is a process. This part did not participate in the reaction. It's retention. It's not changing. Associate to alcohol attack first, and the Cl minus come back and attack. Product is 1 step of SN2 happened. That's why it was included. 이해가 좀 마지막 기회다. Okay, strong base prefers E2 reaction, and here I use PBr3 for this reaction. Is there retention or inversion? Okay.
Inversion.
That's it. Same as this is same class. Possibility different class. Okay, to make the carbocation intermediate stable using polar solvent. Racemization, you lose the specific information. It's mixture of others, 50%. Now, tertiary alcohol product will be active halide mechanism SN1 or E1. There's a tertiary that's ready to form carbocation. It can go to SN1 product of active halide, or it may go to the elimination product, the E1 product. And if goes into the SN1, it is racemization of the reaction SN1. It may not have inverted product. Inverted product comes from which mechanism? SN2, tertiary. SN2 cannot work. I gave you the same question last time. Hard nucleophile. This is a softened nucleophile. Right? Becomes softer and becomes better nucleophile. Palladium is like a Suzuki coupling with the allyl-boronic acid. And I asked you the question of what's the reagent name of this? Okay, this is a Gilman reagent. Korean reagent is a magnesium reagent. Shimon-Smith was what? Shimon-Smith. What is that reaction? 처음 들어? 저 아저씨들 몰라? 진짜 처음 들어? Zinc and what happens? Zinc가 들어가는 거 맞아. And what happens? Zinc is a reducing agent. A little more. Alkyl halide becomes electrophile. Alkyl halide is always electrophile. Nucleophile, that's a Grignard reagent. 찾아봐. Lindell reagent, what is it? Lindell reagent, He2 and you need a little more. Na and 아니고 영원히 한 조각 있으면 내놓을까요? 그러면 Shimon-Smith is forming cycloalkane CH2I2 and zinc, and to remove the iodide, forming carbene and forming cycloalkane. Cyclopropane is a Shimon-Smith reagent. And Lindell reagent, yes, the H2 hydrogenation catalyst. Is it good catalyst or bad catalyst? Bad catalyst. Why it is bad? Stop where? Starting material is alkyne and it stopped in alkene. Okay, we got it. So If you use a good catalyst like a platinum, palladium, it goes to the alkane. Okay, you cannot stop. So make the catalyst a little weaker by adding poison. So stop in the middle in alkane. That's a Lindlar catalyst. Okay? Even though you do not know exact composition of a Lindlar catalyst, if you write down Lindlar catalyst, then okay, I will call. Okay, you got answer. Okay. Okay, so this is a summary of the last week. Now we are moving to analysis. The first one, mass spectrometry. Original plan was there was a player, but she's not here. Okay, mass spectrometry. How do we measure the weight of molecule? Molecule is very small, and the weight, the mass is very small too. But we have molecular weight, atomic weight, kind of a number. Before we go there, how can you measure the very, very small molecule's physical weight? Answer is using mass spectrometry. And what is the principle in there? That's the question. How can you measure very, very small molecule? We know it's very small. How small exactly? Cannot feel it, so it's very, very small. How can you measure the weight of the molecule? If you know the exact number of the molecule, we can collect them. And then enough numbers of molecule. Okay, this is trillion over trillion. And then we can weigh using scale. That's one way. But if you do not know the exact number of the molecule, then you need to measure one molecule's weight. How can you do it? Say again? F equal ma. Okay, F equal ma. Okay, F equal ma. Using this formula, how can you do it? Say again? Attack the molecule. Electron, some attack, and then?
And we check the running time of the molecule.
Running time of the molecule. Okay. Somehow attack the molecule and make the molecule ion, and then measure the running time of the molecule. Running time when? Electric field. Okay. In electric field, and then running time, let's say this is a positively charged one. We may start from here, and this pushes out, and then it will move to this. And then sometimes they have the running time. Is it 1 and 2 and 2 and? Thank you. Running means it should on the surface and it should run like this, right? If it's slow, that's a crawling. If it's fast, that's running. If it's a jump up and it's a running. If I jump up and then running, then it may be a flight time. And this is one way. So sometimes that and combined together with the Helmholtz, in the electric field, if you put those charged molecule, charged small something, ion, and it can move from one charge to the other charge. If you measure those flying time, that's what we call time of flight. Time of flight, then through this formula, if you measure that, and if you change this whole length is fixed, and then if you calculate that length versus the time, then that is related to this mass. True. That's one way. That's kind of a relatively new method, time of flight, but that's tough. You may heard. It's one technique, but that's not the first technique to measure that. Other method, putting those molecules into electric field to make that very sensitive, means very high resolution. You need to get this length longer and longer, right? If it's very short, then resolution may be low. It may be difficult to resolve 12 to 13. If it can be very long, then maybe 12.1 and 12.2 can be measured. That discrimination power we call resolution, 해상도. Okay? So making this length long, that's one way. There's another way. First way of to measure
M overshoots.
M
Overshoots.
of G. What is M?
S.
This is mass. G.
전하.
This is a charge.
Yes.
So now M over G is applied here too. If it is a two charge, then it may move faster. Right? So here what is measured is actually not only M over G is measured. So that's applied here too.
네. 시간 말고 그 전기장에서 휘는 정도.
Okay?
거리고.
In the electric field, if this charged molecule here, then it is curved to where? It may be straight line motion to the other end. There is no curve. 한번 뭔가 봤어? 뭐 휘었다 그랬어? Where it makes the curved motion?
아. 액체나.
In the liquid? 내가 구글 트랜슬레이트야. 영어로 해.
Liquid or gas.
In the liquid, it may be slower. In gas, it's faster. Okay. In gas, it's flying. The liquid is swimming. It doesn't make difference. It doesn't make a curved motion. Where does it make a curved motion? 고등학교 때 다 배웠어. Where does it make a curved motion? Englishman. Side. Put here. On the side.
Like the
Okay. If it is a side here, then it can move to here and push to this way, push to this way. It may move this way. Still, it may be straight line motion. It may not be curved motion.
vertical to movement of
Same story on the side and vertical movement. Still, if you put that here, if it's positive charge, it doesn't move here, it moves here.
Up or down.
Hmm?
Up or down.
Up or down, this is a tube, and this axis versus this axis, same situation. Up here, it move here. It may not be curved motion. You have learned this kind of things. Ah. In the magnetic field. In the magnetic field, FBI, if when you had this Lorentz force, what is the F force? B magnetic field. I, what is I? Current. Current means motion of the charged particles. If a charged particle moves in magnetic field, it gets the force perpendicular to the motion. That's why in the magnetic field, the charged particle is being curved because it is constantly getting those force and make a circular motion. Okay. So mass spec originally it has been developed by utilizing that kind of a property. Then here you can put with this formula, making this the circular motion force and magnetic field force. Among there, we can get same information. So to do that, Now, if I put the question back, if the molecule is neutral, can you use this force? Neutral molecule, two ways, time of flight, neutral molecule inside here, it doesn't feel any force. In the time of flight, the molecule should be charged, either positively or negatively. Okay? In the magnetic field, if a neutral molecule flies, does it get force? No. So that means to use this mass spectrometry, we need to prepare for the sample, and first step is we need to make it into ion. Ionization is necessary. If the molecule does not get ionized, we cannot use the mass spectrometry. Neutral molecule cannot make any motion in the electric force, in the electric field, or in the magnetic field in either case. Okay. Second step is there is a different method of the analyzing. And here one of them is magnetic sector, means in the magnetic field. And second one, already you gave the answer, time of flight in the electric field. And quadrupole is to make this system a little small, miniaturize the system. In the quadrupole, can you guess if this is a magnetic field or electric field? magnetic field. 둘 중에 하나 골라도 그렇게 못 보구나. So first of all, ionization. You need to make the molecule ionized. To make the ion, you can add electron or you can remove electron, either way. If you add electron, that gives you negative charge particle. If you remove electron, positive charge. In the beginning, you don't know. So just to give high energy electron ionization. Just to give high speed electron. Electron is very small. Electron has a different name from negative charge at the end. If you apply high voltage, it generates some ray. What's the name of that ray? Okay, that's a beta ray. That's good. Okay, but that's usually happens during the radioactive molecules decomposition. In the machine, by applying high voltage, you generate this ray. What is that ray? And that has been used to figure out the atomic structure. 음극선. In English?
Electric.
Cathodic ray. Cathode is 음극, cathode ray is 음극선. So by generating that kind of a high energy electron, and then bombard the molecule. And then electron bombard, if you kick it out one electron, then it becomes positive charge. If that electron is observed by the molecule, it may generate the negative particles. So it may generate both. So anyway, once you have this kind of the charged species, in this case only electron is moved out or moved in, that becomes a charge, but at the same time there is a radical too. Because only one electron also changing. Okay. So radical cation, radical anion can be formed. That one now, first step job done, ionization done. Then next step is analyzing. By putting into magnetic field. And you can design this kind of a tube, and by approximately measuring those force, and then you generate ionization here by giving strong electron beam, and the ionized materials are shoot inside here. Now it's moving to this way. Once it's moving, then there's getting the force, Lorentz force, and it starts to generate this kind of a motion, curved motion to go here. If it's heavy, then it goes bigger circle. If it's smaller, it makes a smaller circle. And then you measure those distance. Those distance by putting into this formula that you can get M or G values. So to get high resolution, you need to make this magnetic sector very big. Small one can give you only small, the low resolution data. So high resolution one, it can be quite big from there over there, like filling up the whole room like this. That was high resolution mass spec machines. Now, if you have positively charged one, it goes this way. If you have a negatively charged one, then it goes this way. Then you cannot use this. Then to measure both negative and positive, you need to have two chamber, one chamber here and another chamber next to the row of door to that direction. This single one is already very expensive. And if you need to build another one over there, it could be double price, double cost. How can you reduce the cost? By changing the magnetic field. So using the same chamber, and then applying the magnetic field the opposite way, then now positive will move this way. If you change it, now negative particle moves this way. That's much cheaper way. Just by switch, those magnetic bar like this. Then ready to measure negative charge. But anyway, that implies that you cannot measure both positive and negative together. Right? You should choose only one. That's why if you get the mass spec data, then you should check whether this is a negatively charged one or positively charged. Okay. Quadrupole. Now, one method is a long tube of electric field. The other one is curved magnetic field. Okay. Now, if this is a shoot, it's right here. And then if it's a two-pole, positive, negative, what do you call this? I can highlight positive, negative. This pole is dipole because it has a two pole. If it's a four poles usually is positive, positive, and negative, negative. This is what we call quadrupole. And if the particle is moving in, shoot into the electric field, if it is a positive charge, then goes in, and then if this is negative, then it may not go here, it may go here or here, and hit the wall. But if you change this negative to positive very quickly, positive, negative, positive, negative, positive, negative, changing like this, then inserted particle can go here and then attracted to this, and then attracted to this, it makes circular motion and then move forward. By controlling those frequency, how fast they change those charges, and the M over G value, if it is perfectly matching, then it can go through, and then exit through this and go to the detector. If it's too fast or too slow, then in the middle, it makes just a hit on the wall. Okay? So to measure this, by blowing your ions through this, you change those frequency of this change from low to high. Then only survived one passes through, and you can scan from low molecule to high molecule. Advantage of this is you don't need to make long the time of flight the channels. This can be very small. By just changing these frequency, you can scan the particles mass. Okay. So altogether, these two. Together, if you call the mass spec's name, usually it gives you two names. One is ionization method, and the other way is analyzer method. So you have a mass spec machine. What kind of mass spec do you have? Then most likely what you hear is EI quadrupole. ESI, magnetic sector is now very popular these days. ESI, top. Mildly top is what we hear. Okay? How you ionize it, and then how you analyze it. Ionization method and analyzer name combined together. Sometimes you combine this mass spec machine, two of them together. One analyzed, and then quadrupole select only one mass molecule, ion, and inject into second mass by breaking it to analyze the further information. Then this can be combined together. mildly Q-top. First step is photophore selected, and second injection into the top. Or mildly top. One top and another top. Or quadruple. So that kind of combination is also possible. Okay? This is how you can understand the mechanism of necessary. Now by the result, you can get this kind of spectrum. Here, this is the M over G value. And if this molecule propane is injected, molecular weight is 44, then you can see, okay, 44 here. And this is the biggest molecule, this is the mother, the molecule's mass. But at the same time, you see some fragmented one. What's the difference between them?
음,
44 minus 29, 동호? 커피 한잔 사줄까? 영현아? 15. What can be 15? CH3. Carbon is 12. H is CH3 is 15. Means maybe it can be fragmented. One methyl group is removed. That can be visual here. Ion, the electron ionization, this is a very high energy electron. It hits the molecule, it breaks up the molecules. So if you're lucky, then you can save the mother. But in many cases, you see it fragmented the molecules. Now, 2,2-methyl-propane or neopentane, and this one, molecular is 72. Even sometimes you cannot see mother molecule because it's already broken. And 72 minus 15, what's it? 57. If it's one more breaking, minus 15 again, and may form something like this. So this one, in the beginning, it forms maybe this mother, but it can be break down, and then minus 15, and further breaking down here, and then making this. So it can generate several peaks, small ones. Now hexane, 86. So that's the vibe. There's this peak, and then what happened here? Minus what?
에틸.
It's 15, 14, 29, minus 29. Okay? That means it's breaking down, depending on where is the breaking, and it forms minus ethyl, maybe in the middle, forming in the middle, propyl, and a different fragment. So by looking at those fragmented pattern, you can guess what is the original structure. So before NMR was the NMR was invented, and mass spec was very important tool to figure out the organomolecules structure. So using this method, let's say, now by looking at this molecule, what is the degree of unsaturation of this molecule? 1. If it's 1, then either it may have a 1 double bond, or it's a cyclic structure. So here are two options. This is a carbon 7, so methyl cyclohexane, or ethyl cyclopentane. By looking for the structure, can you guess which one is which? Mother source is 98. It's here.
in sample A is 에틸 펜틴.
Because
앞에서 봤던 거 비슷했어.
okay, good guess. If you look at all the structure, this is a mother, and then this one looks like the methyl is also broken, and this one is ethyl jumped.
Yes.
Two molecules are jumped. So probably quite a good guessing like that. So using that kind of information, you can guess what the structure of the molecules. Now here, if there's any alcohol in the molecule, then breaking pattern is not random. So it's a pattern breaking here, so-called alcohol at the cleavage. And then alcohol side is charging, the other side is relative. This is common. So here you can see this ion, or breaking here, this ion. That's what you can see. So mother is 88, it's very small, it's difficult to see. And then or if it is alcohol, dehydration also happens. And then generate this, then you can see minus 18.2, this is minus 18. Water molecule is removed. So breaking here, or water is removed. Several things you can guess, but as you can see here, this is sometimes quite difficult to, by looking at this is a very complicated process. For a long time ago, this was the only way how we can analyze the organic molecules. Now let's move to the nitrogen. Nitrogen, if you look at this, if it is a breaking, you may guess it may break similar to oxygen. It may break here, or here, or here, and those charges on nitrogen side. So this part is removed, and you may see this minus 29 from 101 to minus 29 is kind of big, you can see. So now, moving to the chloride. Ethyl chloride. Ethyl chloride is 64, but here, the molecular weight of ethyl chloride is 64.5. If you use Chemtrol to measure, okay, one more carbon method. Anyway, if you put the ethyl chloride, and then you may get two numbers like that. One is the exact mass, and one is the molecular weight.
Yes.
What's the difference? If I convert this here, exact mass is 64, and this will be 64.5 or something. Isotope. Then, which one is isotope? Can you explain what's the difference between these two? Weight is
평균.
average of those isotopes.
Yes.
Chlorine's isotope 35 and 37,
Yes.
and the ratio, which is higher? 35 is higher. That's why chlorine's atomic weight average is 35.5. Okay. Then molecular weight is the average of that. And but in the mass spec, those two particles can be recognized separately because they have a different MOG. That's why if you inject that this molecule here, there is 64. There is no 64.5. 64 and 66, two peaks you will see. And the ratio 3 to 1. Okay. This is kind of evidence of the molecule has a chlorine. Okay. Now here, by looking at those isotope numbers, what is the standard of atomic weight? Usually we have hydrogen 1, carbon 12, oxygen 16, a kind of approximate number there, but that's not exact 1.0. Hydrogen 1.0008. Carbon 12.01. Then what is the standard or what is the reference?
12
Carbon 12 is the reference, but carbons at the average number is the 12.01. That means if carbon is composed of 12 and 13 mainly, then what is the ratio between them?
AP versus base 1.
Approximately? So the standard was we chose one isotope, carbon 12 as a 12.00000. That was the standard. And then based on that, we tried to match those different atomic weight. So that's why most of those atomic weight is integer number. 78, 79, something like that. And mixed together of different isotopes by their ratio, we can incorporate the number. So if it's a 10, then 0.1 means it's about 0.1% of carbon 13 is a mixture. That's why the average of carbon is 12.01. So two numbers possible. Similar things happens in bromine. bromine's molecular weight is 80, atomic weight is 80 by average. But in isotope, can you guess what happens here? 1 to 1, and the value is 79 and 81.
Yes.
Almost a 1 to 1. Okay, that's how you can see this kind of isotope pair. Average value is 165 in the middle. The real value is 1 minus 1 plus. Okay, so that's kind of the evidence that whether it's chlorine, you need to have 2 difference and 3 to 1. If you have 1 to 1 and by 2 difference, that's bromine 79 and 80. Okay, so that's mass spec application. Now let's think about the ionization method. As you have seen here, this EI method is not commonly used anymore. As you can see, very small molecules like hexane or ethyl chloride, those already have a fragmentation. Means that this ionization method is very hard. You bombard with the electron and break up the molecule. So this is quite tough ionization. We want to see molecular weight, mother weight, and even bigger molecules. And most common method is 2, and then one of them is ESI, electrospray ionizations. In this method, you mix together those molecules with soluble acid. And acidic solution means you have a proton attached to the molecules, and then spray, and it forms a small bubble, and that contains a lot of protons, a lot of positive charges. And flying into this ionization part, the next part is analyzer part. Okay. Ionization part you spray and then dry in vacuum, then the bubble becomes smaller, then charge density is higher, and repulsion is increased, and it explodes to make smaller bubbles. And eventually, when it reaches to this hole, almost 1 charged molecule inside, and that is injected here. Then, what mass do you expect? Original mass is M, let's say. What mass do you expect? Positively charged one, negatively charged. Most likely positive charged is a protonated. If it is a protonated, then mass is M plus 1. Is commonly we can expect from ESI by adding proton source mixed together and then dry and make it into 1 molecule, 1 ion, and then inject it plus 1. M plus 1 is most common mass from ESI. And there was no high energy impact. There was no electron beam. It's just mixed together and then spray, and then just their bubble is broken into smaller and smaller, and then there was 1 small bubble was injected into the machine. That's ESI. Sounds like very soft. Okay. Another very popular one is MALDI. MALDI is a matrix assisted laser desorption ionization. It's kind of a little long, but keyword is matrix and laser. Molecule is mixed together with matrix, again acid, like a cinnamic acid, and mixed together and a spot on the bottom. And then laser beam is irradiated, but that laser beam does not need to attack directly with the molecule. That activates, let's say, very small amount of your molecule, and then all others are the matrix. Then the laser beam has a better chance to attack this matrix molecule. The matrix molecule absorbs the light and activate it and transfer that energy to your molecule. And this is an acidic molecule. Most likely, your ionized molecule could be also very easily protonated. And it can be maybe 1 proton or 2 proton. Multi-numbers of proton can be transferred to. Okay. Anyway, this is kind of very soft another method. Now this method is, this is a MALDI spot, MALDI target. you can spot those mixture of solutions on here. Means you have a molecule mixed together with a ceramic acid, something like this, and make a drop and then spot here. Then you can measure how many, 10 by 10, maybe 100, maybe several hundreds of spots you can make. Sample 1, tone 1, answer 2, kind of your spot, and then submit it. Then the machine read it like and then check one by one. Can be quite fast. So this is MALDI. Now, if you want to connect this mass spec machine to HPLC, HPLC is a high performance liquid chromatography. You have a mixture, you inject it to HPLC, you can see different peaks. And that is coming out from the column. And if you want to inject that directly to mass spec, then which method may be better, MALDI or ESI? MALDI because 어떻게 둘 중에 하나 고르는 건 그렇게 못하냐? If you need to use MALDI, every spot you coming out, you should spot one by one, right? If it's a 30 minutes run, then even every 1 minute you spot one by one, then you can do it. In comparison, here, HPLC generated those material, all you need to do is just mix together with the acid and just keep spraying. That's easier, isn't it? So usually, HPLC is connected to mass spec, what we call LCMS. It's also a very common method to analyze. If you do organic chemistry, organic synthesis, maybe TLC is one way you can do. But if you inject those reactor mixture directly into this machine, HPLC several peaks, and each peaks can be injected directly to the mass spec. It tells you the mass of your molecule. Then you can easily guess which one is your starting material, which one is your product, and which one is your byproduct. So that means if you configure those machines, LCMS wanted to be your option, then LC, ESI, something. If you choose LC MALDI, then you need to spot every samples on this one by one. It can be faster too, but comparing to ESI, this takes extra work to do that. Okay. Yeah. Through this software ionization method, now, not only those small molecules, even enzymes, proteins, very big proteins, 14,000 molecular weight. In this case, this is a molecular weight, 14,000. Either MALDI or ESI, you have a chance to see the kind of big molecules without any breaking. Now this is so powerful, so EI is not in real world anymore. And most of those are the mass spec machines these days. Either you use ESI or MALDI. Okay? But your textbook is a little older version, and to tell you those fragmentation information, that information was included, but that's kind of a history. Now using this, you can see different things here too. If you look at this one to this one, what's the value? Almost double. If it's double, what does that mean?
Charge.
If the charge is doubled, mass is 14,000. If the charge is doubled, then you should see 7,000. This big, maybe half. This is double.
Mass
Maybe that's that peak. Maybe that's diameter of the proteins. This is a monomer and this is a diameter. But key point here is, important thing here is this one. If you see this peak, then this is almost a half of this. And maybe that's 2 proton is added. And it is 2 charges. That's why divided by 2, that make in this range. So that means in the mass spec, I said magnetic sector, it needs to have a very big machine. To get this high molecular weight, you need to make time of flight length very long or magnetic sector very big. But if you can see this kind of a multi-charged one, then even detector does not need a so big. Detector can be only this range, still it can cover these molecules. Now the problem is we need to figure out whether this is a 2 plus or 1 plus. How can you know whether this peak is really 2 plus, not 1 plus? 유준아? Using the information you learned today. How can you figure out whether this peak is, let's just say this is 1 plus and this is 2 plus. How can you say this is a 2 plus? I intentionally show you this picture. 제발 좀 맞춰줘.
질량이 질량의 절반이 되는 이상.
But if you don't know your mother's the molecular weight, then you don't have a way to say whether this is a half of your target molecule. My question is whether this is a 1 plus or 2 plus. How can you say? The charge is a 2, not 1. How can you say?
아, R에
아래.
저 MOZ
MOZ.
값이 나왔는데
So this value is always there. If you have the machine, then the value is always there.
So
Isotope.
the other peak, M plus 1
Other peak is m plus 1, and this peak is isotope peak also that gets half effect. So this one is, let's just say, 64, 65, 66 you receive. If it's a half of them, then this is, let's say, 30, 30.5, then 31. Then isotope effect is also narrow. Makes sense, right? If it's a 3 plus, then you will see 30.3, 30.6, 30.9 or something. That isotope peak is also can get narrow. Right? Atomic weight is a 1 difference each. So that's why if it's a plus 2, half, plus 3, 1/3, kind of changes in the experiment. By looking at that pattern, then you have a chance to figure out whether that's a plus 1 or plus 2. Okay, so this is the general introduction of mass spec. Again, if we summarize those mass spec configuration, most common the analyzation method we use right now, ESI or MALI. And then analyzers, quadrupole, time of flight, or ion trap, we didn't learn today, but that kind of a combination is very popular. And to make those machines together, mass spec is connected together. Then top, Q-top, QQ is usually you need to have one more Q in the beginning, in the middle, to break down the mother, the peak. So triple Q, kind of a combinations usually you can see. Okay. Multi top. If it's a LC connected, most likely LC, ESI, top, ESI, quadrupole. Okay, so we are going to learn on Thursday IR spectroscopy, and next week NMR. NMR is so powerful, so all other machines are becoming a little secondary by the method. But the method of the mass spec sensitivity is very, very powerful, and then this is quite the important information. Is good to know. Okay, any question for mass spec? Okay, then Boyan will come back with the IR presentation next time. Right? Okay, we got it.